All right, this is kind of at the beginning, I guess, of any refresher that you might want to do for mathematics. Just going to review in this little series of videos, just review some basic stuff, kind of get you up to speed. So let's start off with numbers. And go up here and see if I can get a straight line. And I'm doing this with a digital pen. Okay, so we're just going to draw a straight line here. And let's put a mark in the middle. There we go. And let's call this the number line. And we'll put some tick marks here. And this big tick mark in the middle, let's label that 0. And then we'll just go along with the grid that's on my drawing paper here. And we'll just label this 1, 2, 3, 4, 5, 6, and it goes on. Matter of fact, it goes off this direction toward positive infinity. And we'll label this one -1, -2, -3, -4, -5, -6. And similarly, we'll head off into this direction toward negative infinity. Infinity is not a number. It's undefined, really. If it were a number, we could add 1 to it, and that would, of course, destroy the whole idea of infinity. It just represents a case, I believe, or perhaps a state. Anyway, this is all in the real number system. And maybe that implies that there might be other systems, and indeed there are. If you were to divide all of the numbers, and let's put them in this circle, we could divide this circle in half, and on one side we would have the real numbers. That's the symbol for real numbers, the double backbone line there for R, and the other are the imaginaries. And we'll symbolize that by the square root of -1. Imaginary is such an unfortunate name. And even in amateur radio, you will come up against some of these. In normal math and arithmetic, for business and science, medicine, or whatever, negative numbers are not negative numbers. Imaginary numbers don't come into play that much. But in physics, and of course electronics is a branch of physics, we get into this realm of imaginary numbers. But I'll talk about that separately. Maybe in another video or the end of this one. We're going to be concentrating solely on real numbers. So all real numbers live here. So we're talking about things like certainly our counting numbers, numbers like the square root of 2, pi. Matter of fact, both of these values are what are referred to as irrational numbers. I'm not big on jargon, but I'll explain this. And of course, there are rational numbers. So what's the difference? Simply put, an irrational number is any number that cannot be expressed as a fraction using integers. So numbers like 2/3, this is a rational number because it's obviously a fraction. So this is rational. The word here that pay attention to, the subword, is the word ratio. A fraction is a ratio is a fraction, and I'm going to do a little refresher on fractions to help you get started on those, because those can be confusing. But rational numbers and irrational numbers, they all live on this number line. Okay, just wanted to give you an idea of the animals that we're dealing with. And then, of course, we have the counterpart. These are negative numbers. If you've had algebra before, then you're familiar with, or at least have heard of, negative and positive numbers. Generally in arithmetic and like business or whatever, don't get into negative numbers much. But in algebra, they pop up all the time. And it's because of how algebra works. They're just as valid. They just go the other direction. Well, let's talk about that. Notice that we start with 0 at the middle of this, and the number line goes off in opposite directions. That may give you a clue as how arithmetic is done doing this. It turns out that when we combine a negative number with a positive number, it's a bit like combining antimatter with matter. They annihilate each other on a one-to-one basis. For example, if I take a negative 1 and a positive 1, typically the positive is not written, the plus sign, but it's always written if the number is negative. If I combine these, and I'll use the addition sign for that, they cancel each other out. So that's good to keep in mind. That can be confusing also. So that's combining. That includes the operations of addition and subtraction. You're not going to have to worry too much about this in any of the exam questions or whatever, trying to work problems with this. I just want to introduce the idea that we do have negative numbers. Because you're familiar with, we can have like 3 dB gain, but we can also have a negative 3 dB gain, which would be basically a loss. But it is going the negative direction. So that's probably about as close to negative numbers as you're going to get. All of our calculations in terms of voltages and currents and dealing with those things are going to be dealing with pretty much positive numbers. So don't sweat the negative numbers too much. The point of this the main point of this video, the takeaway, is that all the real numbers live on this number line. And in that spirit, I want you also to realize that when you're looking at graphs and plots of numbers, and we'll label these axes, we'll say that this is X and this is Y. They may be labeled differently depending on what values you're dealing with. It's common to rename these axes so that they're using variables that are relative to whatever field you're dealing with. The point is that both these axes are real number lines. Okay, and let me finish up the idea here of imaginary numbers and give you kind of a common example of where that would occur. That's not based in electronics, just a kind of a math idea. If you've taken any algebra, you've probably made it through to the polynomial, and that leads us into quadratics. Quadratic equation looks something like x squared plus 2x plus 1 equals 0. And if we were to graph an equation like this, it would make a graph, not this particular one, but any of them would make a graph that might be similar to this. Looks like the top half of a wine glass. I didn't draw this very parabolic, but anyway, it makes a parabola. And the solutions, there are two, where that graph crosses the number line. So whatever number this was or is, and this number, these would be solutions, what x equals. Okay, now there could be a case where we have a quadratic and it draws its parabola, but maybe it does it like this. And notice it does not cross the x-axis. It still has solutions. or roots. The solutions of these kinds of equations are called roots. It does not cross the x-axis. Its solutions are not in the domain of real numbers. They don't live on a real number line. They live on the imaginary number line, which is a whole different plot. In electronics, perhaps one of the biggest areas where we get into this is like in impedance, and we have the effects of inductors and capacitors on an AC signal, and the voltage and the current get separated from each other because of how the electrons are forced to flow through the wire and the effect that those components have on them. And the differences in the phase can be expressed as an imaginary number. So there's an area. In electronics, it's called the J operator rather than I. In typical mathematics, they use the lowercase I to mean that. But since I has an affinity with current, electronics chooses to use the lowercase j. All right, I think that's enough to get started. Don't worry about imaginary numbers and all that. I just wanted to tell you what they were. Hopefully that's rattling a few cobwebs if you're rusty on this. Okay, see you in the next video.